Morning, everybody. Okay. We are continuing our econometric class for today, chapter 3 to variable regression model, the problem of estimations. Okay, I mentioned already in our class that there are two approaches to estimate the parameters. First is ordinary least square, and second is maximum likelihood. Now we discuss about method of least square. Okay, this is our regression model, equation 242, and we get the estimated result of parameters beta 1 hat and beta 2 hat here in equation 262. Okay, and the difference between the actual value of samples and the predicted value of equations is residuals. This is residual in equation 263. This y hat is the estimated conditional mean value of yi. Yi is a sample, the value of sample. Okay, how the sample regression function SRF is self-determined. To see this, let us proceed as follows. First, this is residuals. 311 is a residual, the difference between the actual value and predicted value. The smallest residual means our data are representative. Okay, this line is a sample regression function. Okay, this is in this point x1, y actual value is here. Okay. In the sample regression function is predicted value. The difference between actual value and predicted value is residual in sample per sample. This one is residual for the second sample and so on. This residual are simply the differences between the actual and the estimated values. Okay, now in ordinary least square model, the objective is to minimize residuals. Because residual summation of residual is 0, then residual must be square. So this is 312, it is a square residual. Because our method is to minimize residual, so the optimization process, in optimization, we have two conditions. Optimization. For example, we have y is a function of x. Okay, first is maximization. There are two conditions. First is, we call it first order condition, FOC, or necessary condition. Here, the necessary condition of maximization is dy over dx should be 0. And the second one is the second order condition. SOC, or sufficient condition. The second derivative, d to the power y over dx to the power 2 is less than 0. This for maximization. Okay. Now, for minimization, the second is minimization. Okay, same functions. Same function, we use same function. First order condition. See. Necessary condition. Dy over dx is equal to 0. It's the same for the first order condition. And the second order condition, or sufficient condition. D to the power 2 y over dx to the power 2 is okay. This is a necessary and sufficient condition for optimization, both minimization and maximization. In the first order condition is the same. The first derivative of the equation must be 0, and for the minimization, the second order condition should be greater than 0. Okay, this one is a question 312. This is a square residual. Now, we take the first derivative of the equation 312 with respect to beta 1 and beta 2. Then after rearranging the equations, okay, we get the formula for beta 2. This one a formula for beta 2. This 316, this is a formula for obtaining the parameter of beta 2. Beta 2 hat is n sigma xy minus sigma x sigma y over n sigma x to the power 2 minus sigma x2 square. Okay, this is in the last row for this section 316. It is a deficient form. Deficient form means the difference between the actual value and its mean. Okay. Here, this is a deficient form. The difference between the variable, value of the variable, each variable, and respective mean of the variables. Okay. We have to find out beta 2 before we can calculate beta 1. Okay. You have to find beta 2 first, and then you can construct beta 1 after obtaining beta 2. Okay, beta 1 is in this equation beta 1, sigma x squared times sigma y minus sigma x times sigma xy over n sigma x squared minus sigma x square sigma x. Okay, or y minus beta 2 x bar. Okay, this one, another equation in the exam. Classical linear regression assumptions. Okay, there are some assumptions of classical linear regression model. Okay. First one, assumption number one is the regressions must be linear in parameter. Okay. Linear, we have two linears. The first is linear in parameters. Okay. Linears in parameters. This is first conditions. The equation must have linears in parameters. Another one is linear in variables. Okay. For the second one, we can have the equation has non-linear in variables. For example, here I write down for the cost functions. Cost function is beta 1 plus beta 2 q plus beta 3 q squared plus beta 4 q to the power 3. This is the equation, cost equation plus residuals. Okay. In this cost function, this cost function has linear in parameters, but not linear in variable. However, this model still is still linear regression model. Okay, so the important thing is the equation must have linear in parameters. Okay, any questions for this one? Okay. So this equation 242, beta 1 is linear because the beta 1 has to the power 1. Beta 2 also has to the power 1. So beta 1 and beta 2 are linear in parameters. So this is the first assumption of the classical linear regression models. The second one, fixed x value or x value independence of error terms. Okay, this is very important assumption in the classical linear regression model. If there is a violation of these assumptions, so the OLS model is not valid. So we have to run our model with, for example, system equation. Okay. The second one, the x value must be fixed in repeated samples. Okay, this is very important assumption in classical linear regression model. There is no correlations between error term and independent variable. It's very important assumptions in classical linear regression model. There is no relationship between residuals and explanatory. Okay, this is the most important assumption. If we violate this assumption, mean the OLS is no longer valid. Okay, any question? Any question?
Yeah, I have a question.
Huh? Go on.
I have a question. Yeah.
Yeah.
Yeah. In the first assumption.
The first assumption, then.
Yeah, like linear in parameters and linear in variables. So you talked about the beta 1 and the beta 2. They are like all are to the power, is it 0? I don't know. So like how can you identify the parameters and the variables, like you identify both of them in the equation?
Okay. Here I want to write down this one, this cost function. Okay, beta 1 has power only 1. Beta 2 same. Beta 3 same. Beta 4 same. But Q is to the power 1. Another Q to the power 2. Another Q is to the power 3. That means all B's here are linear. All B's are linear. Because each B has the power of 1. Okay. Different to Q. Q, for the first Q is to the power 1. And the second Q is to the power 3. So it's easy to differentiate which one is linear or non-linear. Okay, for example, we have a production function. Q is labeled to the power alpha and K to the power beta. Okay, this is a production function, Cobb-Douglas production function. This Cobb-Douglas production function, this function is non-linear in parameters because the coefficient of the parameter is a power of each variable. Okay, can you differentiate now the difference between linear in parameters? The important thing is linear in parameter. We can have the equation non-linear in variables, but we must have linear in parameters. Okay, for example, for this equation, this production function can be estimated by using OLS after the equation is transformed into logarithm term. Okay, so we have now the equation, for example, here Q plus that is equal to A ln L plus B. Okay. Now, after transforming the equation into log term, we have linear equation model, both linear in parameters and also linear in variables. This one, the last equation I write down. Okay, can you understand? You get it?
Thank you, thank you.
Okay. Now another assumption in this classical linear regression model, the third assumption is zero mean value of disturbances. Okay, we assume that the residual has zero mean. This is very important assumption because if the residual has zero mean, this means the residuals has distributions. Okay. Okay, here I clear this one. If the residuals have distribution, okay, this means Y has distribution. If Y has distribution, then beta, the parameters, has distribution. If the parameters has distribution, so we can test for the significant this if the residual have distributions, this means Y also has distributions. Okay, if Y has distributions, this means beta or the parameter has distribution. If the parameter has distribution, this means we can apply a hypothesis testing to test whether the parameter is different from zero or is equal to zero. This is the distribution of residuals. Okay. Here we see this here. This is a zero here. We have negative and positive. Okay. Here negative because the difference between the actual value and predicted value. The predicted value greater than actual value, so the residual is negative. Here, upper part of this graph, this means actual value is greater than predicted value. Okay, we have this one. This is the mean of the residual. The fourth, homoscedasticity or constant variance. Okay. Here we assume that the residual is constant from the beginning of observation until the end. So here, the variant residuals, that means that the difference between the residual and residual mean of residual square, this is a sigma square. The sigma square, there is no sign of T or I in this variance. If the sigma square has T or I, this means the variance is not constant of observation. This means variance can be greater in the first observation and smaller, bigger in the first observation and smaller in the last observations. Okay, here we can see this graph represent the homoscedasticity because the difference between residuals and mean residual same from the beginning of observation until the end observations. Okay, this is the case of homoscedasticity. This one heteroscedasticity. Here in the X1, these residuals and the difference between residual and it means is smaller than this one, the second observations. And the second observation is smaller than the last observations. This one means the first out in the beginning, the variance is smaller, and the end, the variance bigger. Okay, for example, we can use the data of populations. The population in the beginning of the year, the population number is smaller, and after some years, the population increase, maybe double or triple, threefold. This means the difference between the first and the last observation become bigger. So this one, the case of heteroscedasticity. Heteroscedasticity can also happen this kind of bigger here, bigger variance in the beginning of observations and smaller in the last observations. This one we can explain, for example, first time we drive a car, we make some accidents, okay? After we are having experience, we can reduce our mistake. So the accident become smaller. This is a kind of heteroscedasticity. Assumption number 1. No autocorrelation between the disturbances. Okay, this one in mathematical notation, covariant mu I and mu J is equal to 0 means there is no relations between first residual and before second residuals. Okay, in mathematical notation, expected value xy is 0. This means that there is no relationship between x and y. Okay. For the case of residual, expected value of mu I, mu j is equal to 0 for I is not equal to j. Okay, for example, I is the year of 2010, whereas the J is the year of 2009. Okay. So, for example, if 2009 there is residual 10 and 2010 the residual bigger or less than 2009. By assumption that there is no relationship between these two periods of observation. Okay, this one is the type of this positive serial correlation, because the graph here from the lower to the upper has a positive relationship, this one negative relationship. C is no residual here, zero correlations, because there is no pattern here. For the C, no pattern here. For A and B, they have pattern here. If you residual, if you graph the residual and the residual like this, okay, or for example, another type of residual like this. Suppose this our data and its distribution is suppose the distribution of data. Oh, sorry. Okay, if we see this the type of distribution by looking at the graph, there is an indication that this data have serial correlations. Here, the first part of this. Okay, for example, we can divide this by 2 parts. Okay, in the left hand side is positive residual, and the right hand side is negative residuals. Okay, any question to here? No, any question? Okay, the assumption number 6, the number of observations must be greater than the number of parameters to be estimated. Okay, this one very important thing. Okay, if you have thesis, you must find the long data to make sure that you estimated results better than the short sample size. Okay. Okay, for example, suppose you estimate the demand for certain good. Okay, this is a function of price of the goods, income, other prices, and we have family size, taste, expectations, locations or districts. Okay, we have location and also dummy for the gender, okay, and so on. So we have here 1, 2, 3, 4, 5, 6, 7, 8. You have 9 parameters. Sorry. 9 parameters. Okay. We need the degree of freedom. difference between observations and the parameters. Here we call it K. Okay. Must be at least 16. Okay. So if we have here 9 parameters, that means we have at least 9, 25, yeah, 25. But 25 is still small sample size. Okay. So now it is better to use, okay, if you okay, make sure this one. Okay. To avoid 2 times you get the data. Okay. Okay. Sample size is very important. Okay. Small sample size will produce the best estimated results. For example, here, theoretically stated that in theory, the coefficient of income is positive for normal good. But you have estimated result is negative. This is the problem of sample size. Another source of sample size. If you have small sample size, you will produce inappropriate estimated results. Okay, so to make sure that you have to find long sample size, longitudinal sample size. Okay, so now it is better to use quarterly data or monthly data. Okay, in FUs we can extrapolate from low frequencies to higher frequencies. Okay, but make sure that only some variables are transformed into higher frequencies data. Okay, this one, the number of observations must be greater than the number of parameters to be estimated. Okay, the number of observations must be greater than the number of explanatory variables. I explained already, if you have 9 parameters, that means you have to extend your sample size. Nature of X. The X values must be different from the sample. Okay. If you are conducting your research, field research, you have to collect your data by separating your samples. For example, if you come to village or any places, don't ask more than 1 respondent at the same time, because you will get the same answer from 10 or more people at the same time. Suppose you ask, what is your income for this average income? And one person said this, I have, for example, 2 million. Okay, 2 million. And another respondent also said that I have also 2 million. This means the income is the same from the beginning of sample until the end of sample. So if you have the same sample, same data, That means you will produce, you will have a multicolor, perfect multicolor, perfect multicolor. Perfect multicolority means you cannot get the estimated parameters. Okay, this one the problem of sample, the same sample value. Okay, yeah. The X value in a given sample must not all be the same. If you have the same sample, means you have the biggest problem. Okay, I have my student learn 4 or 5 years ago. Okay, she got the same case because she grouped the respondent to answer the same question at the same time, and the results is perfect multicolority. So make sure that you have to arrange your research by separating your respondents. Okay, what about these assumptions? The $1 million question is, how realistic are all these assumptions? The reality of assumption is an age-old question in the philosophy of science. Some argue that it does not matter whether assumptions are realistic. What matter are the predictions based on those assumptions. Notable among irrelevance of assumption thesis is Milton Friedman. To him, unreality of assumption is positive advantage. To be important, a hypothesis must be descriptively false in its assumptions. Okay, I have explained for you the important assumption that the X variable must be fixed in a repeated sample. The X has no relationship with the residuals. This is the most important. Okay, for the serial correlation, it is impossible to avoid serial correlations. For example, economic growth. Economic growth has a business cycle, sometimes up, sometimes down. Okay, and also prices. Prices also sometimes up, sometimes down. This is a normal. So don't worry about this assumption unless the problem of the stochastic of X variable. The X variable must be non-stochastic, must be non-random. Okay, if you have random variable of explanatory variables, that means you have to apply other methods of estimations, such as two-state square or three-state square or non-linear regression model. Any question here? No question? Okay. No question? Okay. This one is standard error of least square estimate. Okay. Dia varian beta. Varian beta 2 is a sigma square of a sigma xi square. Xi is a diffusion form. This is standard error. Standard error of beta 2 is square root of varian beta. Okay. 332 is square root of 331. Varian beta 1. Okay. This is one formula for varian beta 1. And square root of varian beta 1 is standard error beta 1. Okay. Standard error beta 1 is used to calculate T statistic. Okay. Calculated T is parameter over its standard error. Okay, this is a formula for the calculated T. Parameters of its standard error. Okay. For beta 2, for example, beta 2 is equal to beta 2 of standard error of beta 2. This is calculated T for beta 2. Okay, this one. Okay. Variant beta 2. This one is square root of variant beta 2. We get standard error beta 2. This one variant beta 1. Square root of variant beta 1 is standard error beta 1. This is variant regressions. This one variant beta. This one variant regression. Okay, variant regression is sigma square over n minus 2. 2 is parameters, number of parameters. Here 2. We have 2 parameters. This means beta 1 and beta 2. In my explanation before, we have a demand function that has 9 parameters. That means k is 9. 2 is k. K is 2. Okay. In this case, k is 2. 2 parameters. Okay. Okay, this one standard error of estimate or standard error the regression. This one covariant, beta 1, beta 2. The relationship between beta 1 and beta 2. Okay, we discussed about Gauss-Markov theorem. As noted earlier, given the assumptions of classical linear regression model, the least square estimate possesses some ideal or optimum properties. These properties are contained in the well-known Gauss-Markov theorem. To understand this theorem, we need to consider the best linear unbiased property. Blue is a best linear unbiased estimator. Linear. What is linear? Linear means that the parameters in the estimated equations have linear coefficient. A linear function of random variables, such as dependent variable y, in the regression model. Okay, we explained already that the beta must be linear. The parameter must be linear. Unbiased. Unbiased, this means the expected value of beta 2 is equal to beta 2. This is ideal. But in the reality, some of estimated parameters are not as expected. What is the best? Best means the parameter has minimum variance in the class all of the estimated or unbiased estimator. Okay, this means this Gauss-Markov theorem, we call it blue. For the Gauss-Markov theorem is blue. Blue. B is best, means the parameter has minimum variance. Okay. L is linear. We explained already this one, linear in parameters. Unbiasedness, value is unbiased. Unbiased means the expected value is the same as the actual. Okay, this is a Gauss-Markov theorem. Best means the variance is minimum. Linear, the parameter must be linear. Unbiased, this means the expected value of the parameters is the same as the actual value, true value, or we call it true value. Okay, any question? No question? Okay. This one, we have two distribution of the beta. Okay. For the A, here A, the expected value of beta is beta 2. It's the same as beta. That means unbiased. But here in A has smaller variance. Smaller variance because the difference between the mean here, mean, and the actual here is smaller than the B. B, this graph of B, panel B, has bigger variance. So A is better than B. This means A is best estimator in the class. Okay, any question? No question?
No.
Yeah. No question? Okay.
Not from me, sir.
Okay. So I want to show you how to estimate the parameters. Okay. Do you have FUs? FU is solid? No?
No, sir.
Oh. You can find by yourself. Don't ask me, please. Okay. Which anyway you search for yourself to find the FUs. Okay. Okay. Now we can use this data of okay. We use data from Gujarati books. I hope I can send for you the data. Okay, I sent already. You can check in the chat. You get it? Okay, here I use this data. I sent already for the data. Can you get it? Yeah, you get it?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, here table 7A. This U.S. defense budget outlays 1962 until 1981. Why is different budgets? X2 is GDP, X3 is military sales, X4 is aerospace industry sales, X5 is military conflict. Okay, here, because we are talking about simple regression model, this means only one variable. So here, I want to delete this data. Okay, here I delete this one. Okay, we do not need this. Delete this one. And here we have y until x5. Okay, I save this one in my my folder. Okay, for example, ROLS. My name is RunOLS. Okay, finish already. I save already in RunOLS. Okay, then I open this FUs. Okay, please open half, not full window, half window, and open the data also half window.
So sorry, we are not seeing the.
Yeah, wait for this one FUs. You get it?
Yes, yes.
Okay. Okay, I open it half. And then I open the data also up. Yeah. To allow me to take the file. Okay, and then click the file and hold it and put it in the FUs. Sorry, I have to close the data first. Okay, can you see this now? This one file from other folder, and then we can click next. Okay, next. Okay, is the first column is here. Next. Okay. Now, if you want to finish it, this one dated. Dated means our data is time series data. Okay. Okay, and then finish. We need to make format. No. Okay. Now we have variable here. Y. Yes. Y. X2, X3, X4, X5. Okay. And then to run the data, first we click on the dependent variable. Must be dependent variable first, and followed by independent variables. Because we are talking about simple regression models, so we click only two variables. So you can right click, open as equation here. Can you see this? This menu?
Yeah.
Yes,
Okay,
yes,
okay,
we
okay.
can.
Equation. And then here, actually we have some menus here. You have this square to steady square, generalized method of moment, and so on. So because we are estimating about linear regression model. So here, y is dependent variable. In the beginning, we click in the first variable chosen is dependent variable, followed by independent variable. C is a constant. The option here, option ordinary, covariant method ordinary. We have only type this one, which no ways here because only linear regression model is okay. Okay, we have this one. Last time, someone in this class asked me about the probability. Okay, this one we can see here. Dependent variable is y. Method estimation is this square. Date today. Okay, and sample size from 1962 until 1981. This means we have 20 observations here. Okay, this B1 constant is B1, 32 point something, and this is a coefficient of beta 2 of x2 is a 0.03x something. This one standard error. Standard error, I explained already. Standard error is a square root of variance of the coefficient. Okay. Okay. T is coefficient divided by standard error. 0.03 divided by 0.002 something, we get 13. This one p-value probability that we reject is null is 0.00. This means beta 2 is statistically significant. Because in theory, that's if income increase, then expenditure on defense also increase. This means this coefficient should be positive. And the estimated results are also positive here. This means this coefficient also significant, theoretically significant. Okay, this one R square, I will explain you later. This one is R square, adjusted R square. This one standard error of regressions, sigma. This one sum square residuals, sigma square. Okay, this is for likelihood, F statistic. Okay, and so on. Okay. Any question here?
Yes, sir.
Yeah.
And pertaining to this e-views, because we have used it before. There was a time I was running a data, and like when you are running large numbers of data, sometimes it will
Your,
give you
your
when you run.
voice is not clear enough. Can you repeat it?
I said pertaining to these if-use.
You want to purchase the view if use?
No, yeah, I was having a problem with it one time, like when you are running large datas and like the time period and the data. If the numbers are large, like you have a huge number, maybe in, let's say, if you are running a data to do with the GDP or employment, and maybe you have large numbers, like something to do with billions.
I
It
cannot
will, when
understand
you want,
what are you asking me?
yeah, the question is like, it normally gives a report, like an error report saying something to do with collinear, like if you are dealing with large numbers, large figures.
Uh-huh.
So my question is, why is that happening, and how to, prevent such errors, like when we running it on if-use, using if-use.
You want to graph or what?
Like, for instance, when one day I was running the data, like when you are running large,
Your
like,
voice is not stable. I don't know, maybe the problem of internet in your area. I cannot hear
okay,
clearly.
okay, maybe I will write it on the chat.
Okay, it is better saying. Okay, this FUs is more friendly compared. Actually, I used Shazam before in the previous years, but Shazam is not friendly for you because we have to write down the syntax program. The syntax program is not easy, so I use now FUs. But to get the FUs, I don't know whether you can buy original copy or correct copy. I don't know.
Some of us have some of us already have the evils.
But you have? Okay, never mind. Okay. So this one, how to run your data in FUs. This one, simple regression model. So we get here. This is a constant. This 32 point something. This one is beta 2. Okay. Here we see that this result is good because this statistically is significant, theoretically also significant. Okay, any question? No question?
Yeah, I think what my friend was trying to ask is like the values that you have in the report, like the probability or the values for the statistics. Sometimes if you run the if-use, you have E there, and you have
you have E. Okay,
yeah.
Exactly.
Okay,
Yeah.
I understand you. Okay, E. Okay, for example, we get this one. For example, we have estimated result of the coefficient. Okay, suppose here we have beta 1. Number 1 is I call it beta 1. Okay, 0.921 e to the power minus 21, right? That's you mean?
Yeah, so yeah.
Okay, that's me. This one 0.9215 times 10 to the power minus 21. This means you have here one of this one. You have 0, 0, 0, 0, 0, minus this one until 21. Yeah. Okay. 9, 2, 1, 5. You get it now?
Yeah.
This one, the meaning of E. This is the to the power. E minus 21 means 10 times to the power minus 21. Another equation, for example, 2, 9, 2, 4, 1, 6. A to the power 5. Okay. This means you have here 2, 4, 1, 6. Because you have 5, that means you have to add 2 zeros with it. Okay. If you have here 10, okay, here 10 means you have to like this. Okay. You get it now? The meaning of E here? E is 10 to the power of. Okay. Any other questions? No question. Okay. Super. Okay. Determinants, coefficient of determinations. Okay, R squared. Because we have a simple regression model, we use a small R squared. For the multiple regression model, okay, for simple regression model, we use small r here, R squared. Letter case, small case. For multiple regression, okay, this is a conventionally used in econometric. This is coefficient of determinations. Okay. Thus far, we were concerned with the problem of estimating regressions coefficients, their standard error, and some of their properties. We now consider the goodness of fit of the fitted regressions line to the set of data. We shall find out how well the sample regression line fits the data. Figure 3.1, it is clear that if all observations were to lie on the regression line, we would obtain a perfect fit, but this is rarely the case. Okay, generally we will be some positive residuals and some negative residual. Okay, now this is a coefficient of determinations. Okay, this one is perfect. It's impossible to get perfect unless you have same sample size. This one high correlation determinations. This one no determination. This smaller. This one quite high determination. Okay. This one how to calculate. Okay. This one how to calculate the determinations, coefficient of determinations. Okay. Here we have total sum of square is equal to, it's better to, this one explain sum of square plus residual sum of square. Here, total sum of square is explain sum of square plus residual sum of square. If we look at the graph here, this one due to regression, this means explain sum square. This one due to residuals, this means residual sum of square. This is summation between due to regression and due to residual, we get the total sum of square. Total sum of square is explain sum square plus residual sum of square. Okay. This one, we divide it by TSS here. Every element here, we get ESS over TSS plus RSS over TSS. Okay. This means R square is ESS over TSS. Explain sum of square divided by total sum of square. Okay. If I give you question, what is the values of TSS and RSS, this means you can subtract from TSS minus RSS, you get ESS, explain sum of square. Okay. The R square coefficient of determinations run from 0 to 1. Okay. It is a non-negative quantity. Why non-negative? Because it's square. Square of negative is positive. Okay. Its limit are 0 and maximum is 1. Why? Because 0 means no correlations, no determinations. 1 is perfect, yeah, but 1 is impossible to get in the real world. Okay, here I will show you this estimated results. Here. Okay, this one RSS, residual sum of square. Sum of square residual is 1, sum of square residual. Okay. Here we have coefficient of determination 0.9. Okay, we can here this one kind of residual. This is our residuals graph. This one our estimated results. Okay. Okay, this one coefficient of determination. This one adjusted. I will explain you later in the multiple regression model. Also for multicollinearity. Multicollinearity, okay, this is impossible to avoid this multicollinearity because, for example, if you have no money, you have no demand. But if your money increase, your demand also increase. Okay, and the price also increase. This means at the time you have money, your effective demand increase. This means the demand for goods also increase. If the demand for good increase, the price of the good also increase. This means income and prices have multicollinearity. This is a normal in our world. Impossible to avoid. If you have money, you don't want to use the money. It is impossible thing. Okay. Okay, this one table 3.3. Please find yourself. This demand for cell phone. Okay, use for table 3.3 to calculate the estimated results. Okay, this is your assignment for today. If you have any no questions, I stop in this class. I'm waiting for the answer of this question. Please write down and send to my email. Okay, I'm waiting for you until 10:15.
Is your email with the full caps lock, sir? Your name?
No, this one, my computer always produce capital letter. The email is not case sensitive. You can use a small case or uppercase.
Oh,
No, any
okay, sir.
questions?
Yeah, sir. I think we should estimate the evils, right?